Hi, hello, and welcome to section number 7. Woot, 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 woot. Woo! It's a great day. It's a great day. We learn chemistry. So the other section recordings each had an issue. One of them, I had my mic off for about 15 minutes. The other one, I started late, and then my timer was weird. So this is it. This is the last shot. This is probably going to be the one that's recorded. So behave. A couple of announcements to start us off. One, today is the last day for regrade requests for exam 1. So far I've only gotten one regrade request. So legitimately, if you have a regrade request, you can push it through. We just don't want frivolous ones or ones that aren't supported based on lecture notes or other information. So also feel free to email me and ask or something. But yeah, regrade request tonight. Then mid-semester check-in meetings. The first batch of signups have been sent out, and it's going to be sent out in 4 batches over the course of the weekend so that students who scored lower on the exam can sign up first for slots to meet. Even if we are meeting this week, then still sign up for a 10-minute meeting next week just because to have another moment to touch base. The 10-minute meetings, so I set aside 14 hours. I'd really like to meet with all the students in the class just to have a one-on-one touch base. Yeah, I would say come into the meeting with a goal in mind because we don't have a ton of time, and so we're not going to be talking about everything. But either a single study strategy or talking about a single type of reactions, or another thing I like to do is you pitch to me how you're studying, and then I'll give you feedback on that study method of what I think works well, what I think doesn't work as well. In the signups, I have a list of suggestions for things. There's also a space that you can give me some details before we meet, and then I can kind of think about it a little bit before. Other thing was mid-semester feedback. So the lecture and section mid-semester feedback quiz is due Sunday. As of today, I think that they're only 50% complete, and our goal is 85. And the small grade bump is going to be something along the lines of 5 points added to your individual score on exam 2. So if you have not completed it, please do. If you have completed it, remind your friends. Someone immediately put me on phone texting, I know you haven't done this, do it. And it will probably be 5 points, not 5 percentage points, so 5 points out of 150. But in the past, some years we make it, some years we don't.
How many people left?
As of today, it was 50%. So on Sunday, I'll send out another announcement, and I'll have the percentage in it. So I'll let you know. So those are kind of my big course logistic things. We also have help room on Monday, PSAT, all that. Any logistics questions from y'all now that we are 13 days till exam 2?
What?
It's everything through 9.
Oh, you're gonna have
So
to-
it's everything, but we're not going to test you explicit exam 1 questions. So chairs, we're not going to have a specific chair question. RNS, we're not going to have a specific RNS question. Reactions from the first unit, very much fair game. MO theory is kind of in everything that we do. So we're not going to have a naming question again, but it is cumulative kind of inherently. Yeah. You can see our little guy for today's a little carbocation because they do funky things. Let me talk you through kind of the game plan for section. So with this, we have... First, we're going to spend some time on carbocations because you saw some basic rearrangements in lecture, but they do even crazier things. And we're going to talk about some of the crazier things that appear on the problem set. Then we're going to go into a little bit of making alcohols leave. They're not great leaving groups, so we need to figure out ways to boot them out. Then ethers and epoxides, we're going to do a very light touch. Just because I don't think that they're very interesting, and also just to all cards on the table. This is my least favorite lecture, not because I think it's super hard, but because I think it's kind of boring, and the reactions are all over the place. There's not a big narrative. So that's kind of the content side. And then the last 30 minutes, we're going to have How to Study Reactions Part 2, the remix. And we are going to do challenge problem 10, which is a hard synthesis on the problem set together. So that's our general game plan. Yeah, I'm trying to get through, I think we'll touch on 3 or 4 challenge problems today in section. Yeah, totally. Okay, so without further ado, I think we're ready for our first transition. Whoa, oh, yeah. So, carbocations. We saw in lecture 6 that carbocations are stabilized by hyperconjugation, among other things. So, hyperconjugation, what that looks like is we have a sigma bond next door to the carbocation that leans its electron slightly closer to the carbocation, like a, there. You'll get through this. It'll be okay. And when we have a lot of these sigma CHs next door, that can be really stabilizing. So we have tertiary carbocations are most stable, then secondary, then primary methyl. We can also stabilize carbocations by what? Resonance. Good. So now, the lecture 7 new idea related to carbocations is if you can form a more stable molecule, you will, and you'll sometimes do kind of funky things. So carbocation rearrangements is when you go from a molecule having a less stable carbocation to a more stable molecule somehow, typically making a more stable carbocation. So there are two really characteristic ones that we want you to know and be able to spot pretty readily. The first one is if you have a secondary carbocation adjacent to a tertiary carbon. So if you have a tertiary carbon, you have a hydrogen on that. You don't have all carbons. And what's going to happen is this hydrogen with its electrons, in other words, a hydride, is going to move over to where the current carbocation is. Now, when that happens, we have robbed this carbon of electrons. So now she is the one with the incomplete octet over here in our product, and we have a tertiary carbocation. Did we form a more stable carbocation? Yes. So that justifies why the molecule did this. It's kind of like the hyperconjugation there went a little bit too far, and actually it just like all the way pushed over. And it's just like, oh, okay, I guess I live here now. So if we are secondary carbocation adjacent to a tertiary carbon, we have the 1,2 hydride shift. The other one is if we have a secondary carbocation adjacent to a quaternary carbon, this carbon's attached to 4 different things, then an entire methyl group can shift over. We call it a 1,2 methyl shift. When that happens, yet again, we are robbing this carbon, so it has the carbocation, and we go from a secondary carbocation to a tertiary carbocation, a more stable one. These are the ones that are going to be fair game for box problems and synthesis. The other ones that are weirder could potentially appear like mechanisms or conceptual questions, but we would have to give you the product to predict it. Yeah.
Sorry. For the 1,2 hydride, that carbocation, like the secondary carbocation, it already has a hydrogen on it, and then you add another one, so now there's 2 hydrogens?
Yeah, and I just drew out explicitly this hydrogen because that's the one that moves. But we could just draw it like this and imply both of them.
Okay.
Yeah. Mm-hmm. Cool. So I like to think about carbocations is like you are trying to cross the highway. And if you are crossing the highway, you need to look both ways before you cross that street. Otherwise, the carbocation is going to get, a little rearrangement. That's you on the test. This is me counting off 2 points on the exam for you missing a carbocation rearrangement. Watch out. Look both ways. So we saw these kind of straightforward ones in lecture, but now it's time for stranger rearrangements.
Oh my God.
I know. So these are all from the problem set, so all examples, a couple of them from challenge problems, but oh wow, it's just going to keep on going. So I'm going to stop that. So these are going to do things that are not your typical rearrangements. Let's check them out. So first up, if we have an alkene and HBr, we talked about in acids, alkenes are just going to grab a hydrogen. Now, when an alkene grabs a hydrogen, we have a choice. We can either put the hydrogen on the end, on the right side here, and we make a carbocation on the left, or we can put a hydrogen on the left side, and we can make a carbocation on the right. Which do you think we want? Carbocation on the left or right? We want on the left. Why? It's secondary here, so it's more stable. Great. So the carbocation that we get is like this, a secondary carbocation. Now, classic rearrangement style, we see that we are adjacent to a quaternary carbon. So we could do a methyl shift. Like that could happen, where this sigma CC goes over. So if we do a 1,2 methyl shift, then our carbocation looks like this. And we have robbed this girl of electrons because we took away its bond to the methyl. So that's where our carbocation is. So now it's just like what we expect, tertiary carbocation, it's more stable. And so at this point, our bromine can come in and attack, and we get this product. But there's another option. So this carbocation is also adjacent to a ring, this 5-membered ring here. And 5-membered rings are not super strained. Like, it's not as bad as a 4-membered ring, but there still is some angle strain by being in a 5-membered ring rather than a 6, which is the stable one. So what we could have is the sigma bond in this ring move over and do the rearrangement instead. In which case, it's not a methyl moving anymore. We would say that this is a 1,2 alkyl shift. And this also has a fancy name called a ring expansion, which I think Logan mentioned very briefly in lecture, but I don't think y'all actually saw it. So it expands the ring open. And whenever you get into ring stuff, number your carbons, please. I feel like I'm saying, like, watch your children. Like, just, otherwise it's going to get really out of whack. So if we do 1, 2, 3, 4, 5, 6, we are now going from 6 connected to 2 to having 6 connected to 1. So we're forming a 6-membered ring. So we can just draw a 6-membered ring. And then we can start numbering. Like 1, 2, 3, 4, 5, 6. Now, carbon 1, what else do we need to have on it? A methyl. So there's a methyl that's off of it. And then which carbon did we rob in this orange pathway? We robbed 2. So 2 did have this bond to 6, but now 2 is no longer bonded to 6, so 2 has a carbocation. So interesting. This is a secondary carbocation still. So we didn't form a more stable carbocation exactly, but we did form a more stable molecule by alleviating some of that ring strain. So that's kind of the bigger important idea. But now we have a secondary carbocation adjacent to a tertiary carbon, right? Right? So what can we do? We can do another shift. Because we're forming a more stable molecule. So, the doubling up. Now we have a tertiary carbocation and we've alleviated the ring strain. Lovely, lovely. I would say do these as separate steps. Don't do these all at once. And then as a last step, our Br- can come and attack here. Gia.
Shouldn't the 2 have like a methyl on it? Because we're not doing the green step.
Thank you. Oh my gosh, you're so right. I just deleted her, didn't I? Wow, and I deleted her last year as well. I poofed her. Crazy. Thank you, Gia. Coming to save the day. So actually there wouldn't be a second rearrangement here because this is tertiary. Wow, I didn't clock that in either of my other sections. Can we give a round of applause for Gia? Woo! Saving the day. So, no hydride shift. Because it's tertiary. So why would it do that shift if it's already tertiary, already stable? Great. So the Br- would just come and attack here. So, you have 2 different versions formed. It would not be fair of us to ask you to predict which one is formed from this. But if we drew one of these as the product, we would expect you to be able to supply the curved arrows to get here. And so seeing the product can give you hints as to the rearrangement as well. Yeah.
Could you just go over how you like transformed from what you were given to the second step?
So it all involves numbering the carbons. 1, 2, 3, 4, 5, 6.
Oh, for the green one, I mean.
Oh, everything else is the same. Like this is all the same.
Yeah.
And then I just move the methyl from being there to being there.
Oh, I see. Okay, that's kind of stupid.
No, you're fine. So, the one thing that is not formed is we do not form the product of just attacking this carbocation. So like this thing, it's just probably, it may be a minor product, but we're going to form our more stable intermediates here. So another one that's going to be a little bit shorter. What if we have a carbocation next to a 4-membered ring? Well, she has a lot of ring strain, so she's going to do another alkyl shift and do a ring expansion. So now she becomes a 1, 2, 3, 4, 5. 5-membered ring. And then one needs a little methyl on it. Who did we rob?
5.
Well, 5 went from bonding to 2 to bonding to 1. So 5 is just dandy. 2. And this is where I meant to be like, oh, secondary, our carbocations don't more stable, the molecule's more stable, but our secondary carbocation is adjacent to what? A tertiary carbon. So this is the one where you're going to have the second rearrangement of the hydride shift. I got ahead of myself. That's what happened. So here we'd have a 1, 2 hydride shift. Cool. And now it's tertiary, and we've alleviated some ring strain. Now, challenge problem 6. At some point in the mechanism, you're going to form this carbocation. And this thing looks crazy. So, generally speaking, when we have bridged rings like this, bridge rings are going to have strain associated with them. So, oftentimes you want to alleviate the bridge. Well, we could do that by taking, and you could really do any of these. I'm just going to pick one. We are going to move this sigma bond up and do a rearrangement. Do you buy that? Maybe part of it's hard to see like this, right? And honestly, I think the even harder thing would be trying to draw what the next step is, because it would look cattywampus and all kind of bad. So let's use numbering as our strategy again. So I'm going to do 1, 2, 3, 4, 5, 6. And you see how this is a 6-membered ring? Do you all agree that this is a 6-membered ring? And in our rearrangement, did we break that 6-membered ring at all? No, we just changed how other things are attached onto it. So we definitely in our product are going to have a 6-membered ring. 1, 2, 3, 4, 5, 6. But then let's look at this. 7, 8, 9. We broke a 2 to 9 bond, and we made a 1 to 9 bond. So this is the part that's kind of hard to see, but I'm going to erase this and imagine we have a bond up here. This is going to be a 1, 2, 3, 4, 5 carbon ring. It doesn't look like a pentagon right now, does it? No, but we do see that it has 5 atoms in it, so it should be a 5-membered ring. So using that knowledge, we can just draw a 5-membered ring, and oh my gosh, so much better. And this is 7, 8, 9. So we see 9's attached to 1, whereas before 9 was attached to 2. Okay, when we do this, who did we rob? 2. And it just so happens, based on how I've numbered it, that 2 was robbed every time. But if you number it a different way, 2 won't be robbed. So just make sure it matches whatever your numbering is. So then we have a carbocation here. And now at this point, the reaction goes on and does something like an SN1, like I think an OAC comes and attacks here. And it can also do like an E1, and like a hydrogen can be removed here. Like I think that's what's actually in the question. But hypothetically, and because it's a hypothetical, I'm going to put it in a wacky color. I'm going to put it in... Purple. Which purple, though? I'll put in the lilac kind of light one. 1 second, and then I'll get to it. So, hypothetically, isn't this a secondary carbocation next to a tertiary carbon? So what could happen? Another shift, hypothetically. This is not what happens for the specific problem, and the only way you know that is because in the problem, you don't have the carbocation there. But hypothetically, we could do another shift. And that's why you have to be given the products for some of these more complicated ones. Now, Miss Gia, did I forget another methyl? Okay, what was your question? Oh. Hey, work. Yeah.
Can you just go back to the previous problem again? To that one.
Mm-hmm.
How do you know what hydride is donating to what? Is it the one that's like the hydride on the carbon that's more
Substituted,
okay.
yeah. Yeah. And it's because you want to make a more substituted carbocation. Yeah. Rose.
How do you figure out which number is supposed to be the carbocation?
So, like, your numbering is going to be whatever you number it, but you look at the bond that shifted and look at who's taking the carbocation, or like, who's taking the electrons in the bond to bond with something else. So would it make sense for one, or I keep misspeaking, would it make sense for 2 to steal these electrons and bond to 1? No, because it already has a bond to 1. So the one that took the electrons is 9, took the electrons, bonded with 1. And so who did we rob? 2, who was bonded to 9. So you look at the 2 things that are on the sigma bond that's moving, and whichever one does not end up adding to the other carbon, so in this case 9 adds to 1 up there, 2 was the one that was robbed in the situation.
So that's why 2 is the carbocation.
That's exactly it. Yeah. Because 2 only has like 3 bonds here, and so here it only has 3 bonds if we take away this 2, 9.
And why couldn't we have broken the 2?
You could have broken any of them, but because of the symmetry, you're going to get the same thing no matter what. Yeah. So I'm going to show you one last one that's a little bit weird. So this last one is in challenge problem 3. And challenge problem 3 would otherwise be impossible if it weren't for this one sentence in the instructions. This carbocationic shift is observed to occur simultaneously with the departure of the leaving group. So, carbocation rearrangements, she's the kiddie pool. She's the 1 foot deep. Like, there are rearrangements that are crazy. There are sometimes, like, methyl groups jumping over 13 atoms. Like, it gets into, look up sigmatropic rearrangements when you have a minute. Oh my god, don't get me started. Like, I don't know some of them. You don't need to worry about them. They all have names, like the Curtius rearrangement, the Pinnacle rearrangement, whatever. That's not us. That's not us. And so this type of thing where other girls are moving before we have a carbocation, you haven't really seen her before. You're not really going to see her after for this class. This one problem requires us to think about it a little bit, but they gave you the hint. So look at this. Who left?
And then
Yeah, our N2, and she's going to fizzle off as like an N2 gas, so she'll bubble out. The Chateliers will kind of drive that forward. Okay, so we know that's our leaving group. Our leaving group is going to do what? It's going to leave. So if we broke that sigma Cn, where did we put electrons? The sigma star, the antibond, electrons and antibonds make the bond break. Electrons and antibonds make the bond break. So, if our bond is right here, our antibond is going to be right here. Ooh, sorry. Boop, boop. That okay so far? So now, what is parallel to this antibond?
the hydrogen.
The methyl up here. This hydrogen is a little bit too far away. Yeah, we want like neighbor parallel. And do we also see how the methyl has, the methyl has moved over here. So,
We're gonna swap.
they are. In our rearrangement, since this sigma bond is directly parallel, we're going to have it do its rearrangement and kick off leaving group at the same time. Now, when that happens, this is going to be a little bit interesting. Now, I know y'all are writing things. Can everyone look at the screen for a minute because it's a little bit weird. So, when she rearranges over, she's initially going to be like this. But then we also have a hydrogen that was equatorial here, right? So the hydrogen would be like this. And again, this is right when she moves over. And leaving group leaves. Are these the normal bond angles for this position in a chair? No. So what's it going to do? It's going to rotate downward. And when it rotates downward, it's going to look like CH3 up, H down. And the way that you can think about it is this CH3 is more up than the hydrogen. And so it needs to be in the up position on the chair. So we would draw this as CH3 up and then hydrogen down. The other way you can think about it is like, let's say this is the hydrogen that's up equatorial and the initial one. And I'll draw that out. So our hydrogen is up equatorial. Our methyl is like straight up over here. When she moves over, they're like this, and they bend down. So the methyl is still up, but now it's up equatorial. So it combines a lot of like things here with like chair and everything. But then, this is a bad bond angle, isn't it? Why did I do this? Who did I rob? The carbon here, right? So it's a carbocation. If it's a carbocation, we have an empty p orbital, right? So what's the hybridization of this carbon? And sp2's geometry is what? Dang, you are locked in. Yes, trigonoplanar. So it's not going to be tetrahedral. It's going to be this trigonoplanar thing, which is a little bit weird. Now, what kind of carbocation is this? So close. This carbon's attached to secondary. But is there anything that makes it a little bit special?
Resonance.
Resonance! Oh my gosh! So, look at her. Look at her go. Right here. We have our double chair thing that's not a great chair. They look like little ducks. Do you see how in this resonance structure, does anyone have an incomplete octet? No. So that carbocation, way fiercer than just secondary. No, this is a lovely carbocation. This is a really stable one via resonance. And now to get to our product, all we have to do is we have to remove the hydrogen. And that gets us there. And so that's like half of that challenge problem, where you're doing these leaving groups leaving at the same time as a shift. Okay.
The whole thing you did with drawing the like orbitals for the anti-bonding, is that gonna be like reoccurring?
No, but it's like the reasoning behind things. So like it's something that like on P sets where we're going to need to think through things. Yeah, that's what you're going to need to do. Would we ask you to do this on a test, having never seen it before? No.
But like that's the logic for every kind of like.
I mean, MO theory is the logic for every step of every reaction we teach you. No pressure. And so it's the thing of like, yeah, like the alignment of the orbitals is super important. It's just it's more important in some reactions than the others. Like in E2, the antiperiplanar geometry, that's MO, where we're having to have that like alignment there. But I think it's the way to think about the how of all the steps. Yeah. Yeah. Mm-hmm.
On the first step, why does the CH, like, what does the methyl do instead of, like, an H from, like, next or?
We don't know. It's just in the product we see a methyl is moved. Yeah. Cool. So that's kind of strange rearrangements. Let's move on.
Hey Colton.
Oh.
Is that the 1-2 alkyl shift or no?
So this one is kind of weird because the shift is happening at the same time as departure. So it's not really a carbocation shift. So you don't really need to label it. But you could call it a methyl shift because a methyl moves. Yeah. So. Mm-hmm.
Will we have arrangements in synthesis, in which case?
Only these.
Okay, but would we have to write 1,2 hydride shift in the next step, or?
No, you just need to make sure it's incorporated in your product.
Okay.
Yeah. Because, like, I mean, you're not doing mechanisms in synthesis. Yeah. Cool.
Oh, what's that from?
Time. So, we have alcohol at the party. We want to get alcohol out of the party. What's the organization at Harvard that brings water to all the parties? DAPA something. DAPA. They do that. Yeah, we need to make alcohol leave.
Yeah.
So we have some strategies. The first strategy is a little half-baked in my opinion, which essentially amounts to dumping the alcohol in a vat of acid and hoping for the best. So here, if we have a tertiary alcohol, we dump it in a vat of acid. And when I say acid, I'm talking about acid, like -7 pKa, like acid. Concentrated HBr, hydrobromic acid, hydroiodic acid. Don't mess around. Don't mess around. Don't lose a life.
Not hydrochloric acid.
No, meh. It's a little too weak. A little too weak for us. So here, first step in acid, we protonate the alcohol. Then if it's tertiary, the leaving group can leave, and we can do this little SN1 moment. And once we have an SN1 moment of the bromine, the counter ion can come in and attack. Or if we did it with HI, I could come in and attack. And then now we have an alkyl halide. So we made the alcohol leave. So that works, since via SN1. The other one is if we have primary. We can protonate it. It's now OH2+. And then we can do an SN2 attack with our bromine or our iodine. And then we get our alkyl halide. So I guess one of the big themes of this lecture is SN1 and SN2 showing up in other places. Like we saw it for like GFP kind of initial like alkyl halide reactions last lecture 6 stuff. Lecture 7 is SN1 and SN2 doing other things with other functional groups. And again, it feels a little catch-all, which is why there isn't a clear sense of narrative to lecture 7 in my idea. But it's also like, it's not this class, it's just every time this is taught, it's like this is the hodgepodge chapter where we do thiols, ethers, epoxides, blah, blah, blah. Like, it just is what it is. So with this, why is this bad? Well, one, you're putting it in a vat of acid. So like if you have any other like functional groups on your molecule that are complicated or affected by acid at all, it's going to ruin that. So it's not going to be a great strategy for synthesis, one. Second thing is, what about secondary alcohols? If we did our like SN2 versus SN1, if we have a secondary, it's going to be fair for both SN2 and SN1. So we need some other tools of the trade. We need a more fully baked solution other than our half-baked one. Mm-hmm.
Why don't you just do SN2 then if it takes preference over SN1?
Yeah, it takes precedence.
For a secondary, you mean?
Like you were saying, like, since if they were both fair, like, why can't you still do it if since SN2 is still, like...
Imagine you want to try to control it. Imagine there's a stereocenter at that secondary carbon. If you can't control whether it's SN1 or SN2, you're not going to be able to control the product. So it just gets out of hand. So let's talk about what the solution is, which is we have these 3 other reactions that are going to be a little bit more formalized and standard for making alcohols leave. So with these, the big question for all of them is, in the course of the reaction where we made it a better leaving group, did we retain our stereochemistry at the original carbon, or did we invert it? And if the reaction here involved a step that is SN2 at that carbon, then we say that there is an inversion of stereochemistry that happened. So like for tosyl chloride over here, this oxygen is going to attack the sulfur and then kick off the chlorine. And then you're going to have this protonated version, you just deprotonate it, you're done. Did we ever attack this carbon?
No.
No. So we're not going to have inversion of retention, inversion of stereochemistry. We're only going to have retention. But then over here, the SOCl2 step, and I don't draw out the full mechanisms for all these, I just draw out the kind of key steps. So here, like this is going to attack the sulfur, kick off a Cl. We have OH+, we deprotonate it, we get to this bad boy. And now Cl is going to come in and do an SN2 attack on that carbon. So we get inversion of stereochemistry because we did an SN2 step in there. Similarly, there's a step in this PBr3 one where bromine comes from behind and does a backside attack. And we said that this one in lecture goes on and rearranges into this really stable intermediate that looks like this. You don't need to know that. You don't need to have it memorized. But like both of these have really good driving forces of the reaction. Like this is going to be a stable phosphorus intermediate. SO2 is a gas that's going to bubble out. Both of those are going to drive the reaction heavily forward. So again, the big challenge here is in our alcohol, And we can also do this with primary alcohols, but it's most useful for the secondary alcohols that are fair. We just care about whether or not we want to retain or invert stereochemistry. So when we get to problems like this in practice number 2, suddenly we can play some games. So I'm going to do one of these with you. Do you want me to do the first row, second row, or third row? First row's the easiest. You want me to do the easiest? Third row? I don't... Any of them. Do you want third? Okay. So, let's look at it. Overall, we're going from a dash to a wedge. So, did we have one SN2 happen or two SN2s? One. Because if we do two SN2s, we're going to invert and then invert again, and we'll be back to the original. It's like taking a light switch and go on, off. It's back to where it started. So we only want one SN2 step. Now, we have to get this nucleophile on here. We did a substitution. So what reagent should we use for SH? Well, we have SH with a minus, and we cover up a minus with Na. So we use our good friend Nash. You haven't seen her before, but she's a good friend. She comes in handy. And she is an SN2. So if this is an SN2 step, then our leaving group before this needs to be on a dash or a wedge? A dash, because it's going to invert. So which one of our three goes from a dash and stays on a dash? It retains our stereochemistry. Tosyl. So TSCl with pyridine. So we have OTS. And one thing with that sometimes students get confused on, the oxygen that's originally here is the oxygen in the OTS. It's not a different molecule here. So this one had specifically no SN2. So we only had one inversion overall. So take a couple minutes, try out the other two.
I'm confused. Firstly, why are we only talking about SN2s and not SN1s?
Because none of these reactions had SN1s.
Oh, so the retention is just not a either?
The retention is no SN2 happened.
Okay.
Because SN1, remember, we get a racemic mixture.
Oh, so these,
None of these are SN1.
except for the alcohol one? For the strong acid one?
Yeah.
And you said that this better solution into turning alcohols into a better leaving group before, we only do that with secondary alcohols?
It's most useful with secondary, but we can also do it with primary. It's hard to do with tertiary alcohols because some of these involve an SN2 attack on the carbon.
Mm-hmm.
And so if we had a tertiary carbon, then we're not going to be able to do SN2 on it easily. Yeah.
If we were doing synthesis and not just a simple a line reaction like this, and then we were given a primary or tertiary alcohol, would the best course of action at first be to turn it into a secondary alcohol and then do one of these steps?
You don't know how to do that because that involves getting rid of carbons, which is hard. So generally speaking, if you have an alcohol, for most cases, for 90% of the cases, you are going to use one of these three reactions, and it probably won't be a tertiary. So then, if you've exhausted these, then look at the strong acid version. Yeah.
Can we know when to pick either inversion? How do you know?
So if they give you a reaction, you should know if that reaction had an SN2 or not. So this first one, SOCl2 pyridine, did it have an SN2?
But when it does the light switch closes and then comes back,
Mhm.
it's the same, so you know it's because aren't they both SN2 the inversion ones? Or do you just pick
Yeah.
either?
Between SOCl2 and
Oh, it doesn't matter.
Oh, just the
Yeah, sorry, I didn't understand the question for a minute, but yeah, no. It only matters if you need a bromine for a specific reagent. If you want to make a Grignard, then use the bromine one. Yeah. But actually, also, you can use chlorine with Grignards. You can do,
Great.
I know, you could do MgCl, and she's valid.
That's what
She
I'm saying.
exists.
Oh, that's it.
Yeah. Yeah. why don't we go over it, because I think y'all have had enough time to work, so we'll talk through it. So the first one, SOCL2, does that step involve an SN2?
No.
It does.
Sorry, just joking.
So over here, this step in the SO2 CL2 reaction is going to be an SN2 step at that carbon. So do we need to put our Cl in a dash or a wedge? Dash. Okay, then we have KCN. So if we think about our ranking system for SN2, it's secondary, right? So it's fair. For E2, what's our base strength with CN minus? Good, fair, or poor? Fair. So who wins? SN2. And so we are going to do an SN2 reaction. And now should CN be on a dash or a wedge? Wedge, because SN2 we invert the stereochem. Now, question. If instead of this I had Naomi, then for SN2 it would still be fair. What would it be for E2? Good. So we're going to get an elimination. So we still have our whole GFP framework in our back pocket ready to go. It's a little complicated. Now for the second one, overall, we're going from a wedge to a wedge. So overall, we are retaining stereochemistry, right? So that could mean that we did 0 SN2s, or it could mean we did 2 SN2s. So we have this kind of big idea that double inversion of stereochemistry is retention. Ooh, ooh. Double inversion is retention. But, so, first off, let's start with the N3 over here. So what does our nucleophile need to be? NaN3, because we have a negative charge in N3, and then we cover it up with an Na. That's going to be an SN2 step. The other one needs to be an SN2 as well. So, in this middle one, should it be on a dash or a wedge? A dash. And then we want one of our SN2 leaving groups, so we could use either PBr3 or SOCl2, so whichever you want. I'm going to use PBr3. Also, okay, I'm not a beer person, but I do think PBr is a type of beer, and like alcohol, mnemonic, alcohol, beer, PBr3. I had a student in the first class be like, "What type of beer is it?" And I said, "Couldn't tell ya. I think it comes in a can." So again, we are looking here in terms of starting material to product. Overall, does it look like we retain stereochemistry, in which case that's double inversion, or overall did it invert stereochemistry? And with that, we've stumbled on a wild synthesis strategy. Oh my gosh, oh my gosh. So based on what we want the stereochemistry to be at this site, we can either use the version that makes a leaving group that retains stereochemistry once, and then we only do 1 SN2 total, or we can do 2 SN2s and we get double inversion, which is retention. Yeah.
Or could we just use the one, aka TSCL, without any inversion at all, like with no SN2s?
Yeah, but then you haven't like put CN on here. Like this one, it's like, okay, if we want to go from OH here to a CN, we need a leaving group first. If you just do OTS, then it's just OTS. It's not CN yet.
Right, but you can do OTS and then an SN2. Oh, I see. Oh.
Yeah.
Yeah.
We're,
This little box isn't on there.
it's going to be in the annotated version. I wanted there to be an element of surprise.
Wait, so actually you can pick from any one of these, and then just like, if you need the stereochemistry to be the same, do another.
No, like, yeah, legit. Like, that's why we have taught multiple.
All of them. You can do all of them. At any given moment, you can do all of them.
Girl, you're in outer space right now. If you want, overall, to go from wedge to wedge and get a CN on here,
Yes.
we need to do 2 SN2s. So the first step, where we make it a better leaving group,
Okay.
we need to do one of the SN2 versions. But if we overall want to go from a wedge to a dash, we only want 1 SN2. So when we make it a better leaving group, we don't want an SN2 to happen. We only want an SN2 to happen when NaCN attacks.
You're forcing us to substitute it anyway.
Yes.
Okay.
Yes. Yes. Ding dong.
Clock it.
Work. So now, this one's going to feel like a bit of a non sequitur. But let's look at challenge problem 4, just to knock out another challenge problem. And here, we do see an OH leaving. So, okay, that's in the mix. But now, normally when I ask students what to do here, they start just throwing out things. They're like, oh, pyridine's a base, maybe I'll deprotonate, or, oh, I could do this attack here, blah, blah, blah. Great, love the enthusiasm. Molecules, right? Let's try to do some analysis first and figure out what's going on. So, first thing that I'm seeing is I'm an alkene. So we only know 2 mechanisms for forming alkenes, right? We know E1 and E2. What other things are y'all noticing here just analyzing this? I saw you get ready. There's an alcohol here, but she's not there in the product. Where did she go? Yeah, like here we had an alcohol 1 on each, or 1 oxygen on each. Now we have 2 on the same. Yeah?
It's like the O on the OH is gonna attack the PCl sigma star, and then the Cl will leave.
Ding dong. Where did you see that before?
On the other, like the mechanisms for the other ones.
So, specifically the phosphorus here, too. Like, the other thing to clock here is, like, you haven't seen much phosphorus chemistry. Phosphorus can do weird things. And specifically, it did this whole weird rearrangement, right? Like, so she has expanded octet. We don't know about her. So, with that, why don't we use the PBR reaction as a model for what to do? Since we have a phosphorus here and it's doing kind of similar things. Like, this structure here looks kind of like this one. So, we are clocking the O got moved. We are also clocking a Cl was kicked off. And then it looks like PBR3 stuff. So in the PBR3 mechanism, the first step that we did is exactly what you suggested. Lone pair on oxygen comes and attacks the sigma star phosphorus chlorine, kicks off the chlorine. Okay. So then from here, one thing that we could see is like we have a positive charge. So maybe we use pyridine and deprotonate it, or maybe we don't. Like in the original one here, we left that positive charge on and then we kicked off the OH, right? But let's look at our product. So here, our product had an OH in it, but our product over here doesn't. And so if we have a base present and we have a positive charge and it's going to be a negative over here in the product, I think we go ahead and deprotonate. So let's do pyridine. Okay. So now we need to do an elimination, don't we? So we have a base present. Let's do an E2 elimination. So with this, we get a beta hydrogen next door. And I know we talked about doing E2 on a ring, having to draw chairs. We're not going to make you draw 5-membered chair things. Like, they have little envelopes and like little character ways you could draw it. We're never going to put you in a situation. You can just assume that the position next door is going to have an antiperiplanar beta hydrogen. Yeah. So our pyridine is going to come and do an E2 elimination. And that gets us to our product. So it's that easy. Work. Now with this, I am going to keep on chugging just because there's still a lot to get through. So I'm going to keep plowing. But I think we've covered the main ideas for making alcohols leave. So ethers. That was Wizards of Waverly Place, by the way. Which they just had a reboot of, and actually one of my friends from college is a writer on it. She was like one of the main writers for, yeah. So in ethers and epoxides, I'm going to do a little bit of a light touch. I'm going to move kind of quickly. And one thing I want to start off with is this idea of classifying ethers. Now, this is not like a textbook idea. This is just a Colton thing, a thing that I like to do, that I think makes it easier to work with ethers. So what we're going to do is we're going to look at the carbons on either side of the ether, and we're going to classify them as primary, secondary, tertiary. So this one's connected to one other carbon, so it's primary. And the other one's connected to two carbons, so it's secondary. So I would call this a primary plus secondary ether. So can you try a similar naming thing with the other ones really quick? How'd you do? Cool. So right now it's not clear why we're doing this or why it will be helpful, but we'll come back to it in a minute. So just remember this classifying idea. So there are two main ways we can build an ether. And again, we have this theme of SN1 and SN2 coming back in new ways. We can make an ether via an SN2 route or an SN1 route. And to be honest, the most common way of making an ether, the main one that should come to mind when you think about making an ether, should be the Williamson ether synthesis.
Wait,
I
didn't
don't-
we see this
In lecture.
in lecture 5 though?
No.
Or was that the ester formation thing, the Simpson something?
I
Maybe it was the
think
Simpson.
something like that. But so ether, you should think Williamson ether synthesis. We won't do the call and response, but because there are going to be actually a lot of ways of making ethers, which is really annoying. So what happens is we add NaH, which is a base. She's going to deprotonate our alcohol. Then this alcohol is going to do an SN2 attack on a primary alkyl halide. And then we have an ether. Now, with this, our alkyl halide has to be primary. Because what if she was secondary? Like if it was this structure here. Well then, if we have an O minus, for SN2, if it's secondary, it's going to be fair. But what's it going to be for E2? Good, because we have an O minus. So if we had a secondary, it would just do an elimination here. It won't form an ether. So this side has to be primary.
So it's good SN2.
Yes, so it's good SN2. But then this alcohol could be anything. We could even make her a tertiary alcohol, which is not ideal, but like it can work. So Williamson ether, you can hypothetically use to make a 1' plus any prime ether. That means this side could be primary, secondary, or tertiary. So given that, which of our 4 ethers up here could we have made through Williamson ether? 1 and 3, because we have a primary on one side. So these could have been this alkyl halide, and the other side could have been our alcohol. Now again, this tertiary one being kind of bulky, not great, but still I think that there would be enough yield that it's a reliable way of making ethers. So that's our SN2 route. Our SN1 route, we just need to have acid. So an acid and specifically a tertiary alcohol. So if we have a tertiary alcohol, we protonate it in acid, and then it can just leave and make a carbocation. So then we have our carbocation here, and our other alcohol can come in and attack and make it an ether. You'll have to do like a deprotonation too. I'm not drawing the full mechanisms, but this is a really great strategy if you have a tertiary side of your ether, and the other one can be anything, this one that attacks. So you need tertiary here to be good for SN1 in order for your leaving group to properly leave. So which of our 1, 2, 3, 4 ethers up here could we have made an acid here? 2 and 3, because they have a tertiary side. Work. You can also do things like do an intermolecular ether if they're both on the same molecule. And you're going to look out for other ways of making ethers. You'll learn some in lecture 8. We might even see one later today in section. I don't know. Maybe. How to destroy an ether. Again, same strategies of SN1 or SN2, but ethers are pretty darn stable. Like we do a lot of, like remember ET2O? She was just chilling in that reaction mixture, not touching a single soul. And so ethers not being very reactive means that if we were trying to break an ether, we not only need a strong acid, we need heat. We need to boil that in acid in order for her to fall apart. This is like some taking down Regina George level strategy.
What if she just gets hit by a bus at the end?
This is the chemical equivalent of being hit by the bus at the end. It really is. And so, again, if you are doing a synthesis, you're probably not going to break an ether because there are oftentimes going to be a lot of other molecules going on, other functional groups that are going to be, yes, you're exactly right. You're going to go through some difficult times with a strong acid. The other thing is secondary ethers. This one we didn't say was good to make either strategy of making ethers. Like we didn't say that this was good for Williamson ether or it was good for acid ether synthesis. And it's because it's going to be fair in our SN1 and SN2 ranking. So the PSET's going to explore a little bit more nuance around this. You know how we love nuance here at Harvard University. But I'm not going to talk about that anymore. So I'm going to keep plowing ahead. We're not even going to do transition music because we're just doing a light touch. We're just here and oh my god, suddenly we're at epoxides. Wow. Epoxides, they're cool. They're the most dramatic functional group. They are doing explosions. My favorite fact about epoxides is their IUPAC name is oxiranes. And so I just like this like dramatic, I'm going to explode. I'm going to do all the thing. Okay, oxirane, calm down. Like, yes, the government name of epoxide is oxirane. So we only know right now one method for making epoxides. You're going to learn another one in lecture 8, which is one of my favorite reactions, so be on the lookout. But we start off with this functional group called a halohydrin. Can you say halohydrin? Halohydrin. Halohydrin. This is one that people really, really have a hard time spotting because it just looks like two friends next door, you know? But just like for an acetal, where we have two ORs on the same one, these are not just two ethers next door. Being together affects how they react. Yeah. These are also on adjacent carbons, which is kind of weird. But we will see that this idea of having two functional groups on adjacent carbons is really important, especially for synthesis. So that's going to come back later when we do our big synthesis. So anytime you need two functional groups on adjacent carbons, be thinking epoxide land, be thinking halohydrin land, all of that. So what happens is we add NaOH, a strong base, deprotonates her, then she does an SN2 backside attack, bada bing, bada bang, oxirane. So making epoxide is pretty easy, but breaking them open is a little bit harder. So essentially, a nucleophile is going to come and attack and break one of the sides of this ring to bust it open. So epoxide opening, there's a lot can go on. And for this, I did find a meme that I really liked, but it was a little bit too grainy, so I had to typeset it myself, which felt incredibly nerdy. So when we are busting opening an epoxide, you could say we are cracking open a cold one with the boys. No. Here we are. Thank you. Because here, yeah, like, do you know the phrase?
Like, opening a cold one?
Cracking open a cold one with the boy.
Like it's just understand.
Work. So, getting back on track. So, if we have a fully symmetric ether, and when I said ether, I do mean epoxide. If our epoxide is fully symmetric, then it doesn't matter which side our nucleophile attacks because it's symmetric, right? But when we have an asymmetric epoxide, where one side is more substituted than the other one, then we want to be able to control which side we attack. So the way that we control it is whether or not we open our epoxide in acid or base. So let's start off with acid. So if we were in acid, the first step that we're going to do probably is protonate. Yeah. So we protonate our epoxide. It has a positive charge here. And when this oxygen has a positive formal charge, it's going to make this dipole even more extreme. So these partial positives are even more pronounced. But now, between these two partial positives, which do you think is more stable? The one that's on a tertiary carbon or a secondary carbon? The tertiary. And it's because it has more hyperconjugation. And so what happens is our nucleophile is going to come in And it's going to attack the carbon on the more substituted side because it's the one that has the more stable partial positive charge. Now you might be thinking, Colton, wait. In the past, we've said if our partial positive is stabilized, it's going to react less.
Yeah.
You saw that with carbonyls, right? So the thing that's happening here is if we have a partial positive charge here that's stabilized, this bond can kind of start breaking earlier. It can become more of a hypothetical bond and become more like a real carbocation, which means that our nucleophile can go and attack it easier. It essentially means that this bond is going to break more easily. And that's why we attack the more substituted side in acid. So what we see here is when we have a nucleophile of like alcohol in acid, our alcohol is going to attack the more substituted side, and we add our OR on this more substituted side. And then the oxygen that was in the epoxide just becomes an OH on the less substituted side. Similarly here, our nucleophile is going to be water. We're an acid, so we attack the more substituted side, so we add an OH over here from the water on the more substituted side. On the less substituted side, we have the oxygen from the epoxide. Yeah.
Why wouldn't we, like, what's the case that you said before where we saw that it was the opposite of, like, why wouldn't we attack the most substituted side? Isn't that always what we do?
No, it's related to like carbonyl things in the P set. Let's get into that later, just because to keep this straight. So acid, we're attacking the more substituted side. Our nucleophiles are adding on this more substituted side. But then when we're in base, the biggest factor that affects where the nucleophile adds in base is just kinetics. And so in base, it's just simply faster for the nucleophile to attack the less substituted side. So if we add NaOR, like OR minus in base, then we're attacking on the less substituted side. Similarly, if we add a Grignard, which is also basic, we're adding on the less substituted side. And then for both of these, the oxygen that was in the epoxide goes to the more substituted side. So now let's look at our products here. So when we reacted with alcohols, what functional group did we make? An ether! Another way of making ethers! Oh my gosh! Other than Williamson ether, other than acid, yet another way of making ethers. They keep popping up like weeds. Yeah, you're going to see more in lecture 8, so she's coming back. But importantly, it's an ether adjacent to an alcohol. So we still have another functional group. Now, we also have, if we react with H2O plus, 2 alcohols that are neighbors. She's called a vicinal diol. Diol, like 2 alcohols, and vicinal, like in the same vicinity. That's compared to if you have 2 OHs on the same, we call this a geminal diol, or a hydrate. And this is like Gemini. So geminal diol, vicinal diol in the same vicinity. And then the only one that's a little bit weird is here, when we attack with the Grignard, notice we've added a carbon here, but that's not a functional group. So, something to just think about. The other thing here is the stereochemistry. So, if our epoxide is on wedges, it's going up from the plane of the ring, we are going to be attacking the antibonds of these sigma bonds because we want to break the bond. So our nucleophile in both cases needs to attack from below the ring in order to access that antibond. So what we see in all cases, acid or base here, is since our epoxide is on a wedge, our nucleophile adds on a dash. It adds from below. And it would be the exact opposite. If our epoxide was on a dash, then our nucleophile would add on a wedge. So we have to think about our antibonds. And with that, I am going to move on. I'm still like over for my allotted time for this section. I know that I moved pretty quickly through this. There's some practice here that I just made, some extra practice with epoxides and ethers to try out on your own. But this, I think, is going to be a really helpful like infographic to study and review of like the why it all happens, the stereochemistry, the regiochemistry of where things add. And it took a long time to make, so please use it. Like this alone probably took like 4 or 5 hours the year I made it. Well, because thank you. But like getting these Y's to line up, getting this to be perfectly symmetric, it's ChemDraw is the bane of my existence. But
They should pay you.
Yeah, for real.
Yeah.
You should
Well,
sell these.
but they do pay me.
No, I mean ChemDraw should.
Oh.
Should be an ambassador.
Yeah, like,
Using
you should
their
I need to be a brand ambassador for ChemDraw.
No, not like as a tattoo.
Wow.
I hope I'm gonna figure that out. I meant like ChemDraw should.
Yeah. Well, again, y'all haven't even seen my like magnum opus for the ChemDraw thing, which is for
Serial
lecture
that
8.
you showed us, that gave us a sneak peek.
That's lecture 8.
I'm gagging. So that's
That's
next
lecture 8. Yeah.
Oh,
You've already learned a few of them. I think you've like learned these 2 so far, but you'll learn the rest in lecture 8.
wait, that's fine, guys. We got this.
You do. You do.
Who's we?
So, let's talk about how to study reactions. Part 2. So you remember the first time we talked about this, we talked about studying at different levels of depth, which I think is an important idea to bring into your studying. But now I think the issue is we are just piling on more and more reactions. And so we need a way to kind of internalize and memorize these reactions in a way that's time effective and also is going to help you for how you're going to be tested. So there are a lot of strategies that you've used in other classes that have worked for you and that you probably used for the first exam. So some people rewatch lecture notes, or rewatch lectures, rewrite their lecture notes. Some people make flashcards. Some people make study review sheets. All of those are great strategies when you have time. Do y'all have time?
No.
No, we are like plowing through all this. You have so many problem sets. So we really need a time-effective way of studying these reaction basics. And also a lot of the methods that y'all use to study, methods that feel good to study, are ones that don't require much active learning. So like when you are like copying down notes again, you have access to your notes the whole time. You know, like you're not having to kind of address what you do and do not know. And it can be really passive. Like you could put on a TV show while you're doing it. Same with like flashcards. When you're making flashcards, I guess when you actually do the flashcards, it is kind of active. But like imagine how much time it's going to take to make all of those flashcards. We need something that's going to be really like pragmatic. So let's talk about the DIEs, the desert island exercises. And last year when I kind of introduced this branding, I realized this was not a universal thing. But did you ever have teachers in past class be like, when you take the practice exam, imagine you're on a desert island. It's like you have no resources available to you. No? Anyone heard this before?
Yeah.
Okay, a little. So I mean desert island not in terms of like what are your 3 books that you're bringing. I mean it in terms of there's nothing there. You need to study when there's nothing around you. So we are going to do a desert island exercise together. What we do is on a blank page, write out the actual reaction on the lecture notes. So write the study materials, write the arrow, do not write the product. So if you are a paper user, can you write this out on paper? If you are a tablet user, can you like zoom in so you see nothing else other than this on your page? I'm going to give everyone a minute to do that. And what we're going to do is we're going to set a 3-minute timer. And then in those 3 minutes, you're going to do 2 things. And do not start until we start the exercise together. 1, you're going to try to draw just what the product is. So thinking at that line reaction fake mechanism level, just drawing the product. And then 2, you're going to try to do the full curved arrow mechanism to get there. Draw all the arrows, all the steps, all the charges. You're going to take 3 full minutes. If you don't know what to do, you are going to sit for those 3 minutes and really feel it. And, you know, it's kind of like microdosing panic of like, it's how you would feel on an exam if you didn't know what you were doing. And it also is really effective fuel for studying if you have to sit with that feeling for like, yeah, especially in the like generation where we like scrolling through things and like moving on.
Yeah.
To have to be forced to sit there is horrible. So we're going to try this. I'm going to set a 3-minute timer. Does everyone have it written out and ready to go? Okay, and the other thing is make sure you try to predict the product first because you want to get practice with that line reaction level as well as the mechanism. So, on your mark, get set, begin. 30 seconds left. That's it. That's time. So, okay. Now, can someone try to time me? Can someone get out their phone? I want to see how fast I can do it.
I got you.
So, can you count me in like 3, 2, 1, go?
3, 2, 1.
Wow. Okay. So I'm drawing my line reaction. I need my Emmy. Okay. Now this is going to go in attack. We get our tetrahedral intermediate. H. We have an O minus. We have NH2Me that has a positive charge. We need to do our proton transfer. And our proton transfer, we get it to a neutral state. NHME. That's our Hemi. M and L. Bonus points for writing that. Not really. Then we need to protonate that and make it a better leaving group. H. So then that's H2O plus. We have our NHME still. Lone pair push kick off. Then we have our double bond. But the issue is we still have a hydrogen on there. So we need to remove that with sol, blah, 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 and time.
50 seconds.
Hey. So I try to get to where I can do all of them in about a minute. Y'all aim for like 90 seconds. But like, do you see how having that on lock means you don't have to do all that thinking when you see it in other places. You just know it. And like, that is a hard thing to build. But when you do this exercise and when the 3 minutes are up, check it, open your lecture notes, see how you did. Grade every arrow, grade every charge. Be really honest with your self-reflection, more so than just did you get it right or wrong. Think about why. So if there was one step in here where it took you like 30 seconds out of 3 minutes and you were just on that step and you got caught up, figure out what made you stop there. Like, what was it that was not super intuitive about it? That's something that you may want to like ask a question in like lecture or help room about and like clear that up. Or it can really just like reveal the parts of it that are kind of insecure. Use that as information, then close the book, get a blank page, do the exercise again. Almost any reaction, by the third or fourth time, you're going to be getting most all of it, if not all of it. And this, I think, is just a really, really great time-effective, no-nonsense way of getting these basics down of the reaction. The other thing is, it's active learning. It's really confronting you with the blank page of the exam like you're really going to have. It's not just passive copying notes. It gets you to engage with that feeling of what you do and don't know, and you're actively working on it. A lot of students see this, and the first time that I talk about it to them, they're like, okay, that's going to be my test for have I studied the reactions at the very end, right before the exam. No. This is a tool to help you learn it. Doing this and failing this as a test is very valuable because it tells you what you need to know. And so use this to learn it rather than a test of have you already learned it. Does that kind of make sense? I'm going to keep going and then I'll get questions at the end. So that's phase 1, getting the basics of the reaction. But then there's another part of your studying that needs to be worked on because a lot of you probably studied the reactions from lecture 3 for exam 1 and got really good at doing the reactions just in the lecture notebook. But then it was hard to see it in other places, right? Like, we need to also work on the skill of translating the basics of a reaction onto other chemical situations. So the way that we can work on this generalization is get a different alkene. I said alkene. Get a different carbonyl and a different amine and do out the reaction yourself. It should be the exact same curved arrows as the original reaction. The thing that's changing is just our R groups on these functional groups. And so do this until you go from feeling comfortable with the reaction to being confident. Like, get to the point where you could do an intramolecular version of this, where you could do it on the same molecule, and that doesn't even phase you. And then do the products, do the reverse reaction, go backwards. But do you see how, like, you can do so many other, like, building on this exercise in order to prepare you for how you're going to see it in a bunch of different varieties on the exam. So my big plug for this is 1, active learning the whole time. 2, the time constraint. You're not letting yourself spend 40 minutes on one reaction and then it derails while you're studying. It's 3 minutes, you get feedback. The other thing I like, it's really flexible. It's a 3-minute exercise. If you need a little bit more time than 3 minutes, make it a 4-minute exercise. If you know what you know after 2 minutes and the last minute you're just sitting there, either done with the reaction correct or not done, not knowing what to do, make it 2 minutes. Like, tailor it to your needs and your studying. Either way, I think it's a much more flexible study method than I'm going to make a review sheet of all the reactions or I'm going to rewatch an entire whatever. The other thing is I just think it's pragmatic. Like, again, other ways of studying can feel good, but they aren't the quick and dirty, get what you need to go so that you can move on and, like, work on the next problem set and everything. So, how many people are, like, willing to try this out? A little bit? A little bit? Just try it and see. And when we have our 10-minute meeting next week, be like, hey, I tried this out and it worked for me. Or I tried it out, it didn't work for me, and we can think about other strategies to use. But, like, I would like everyone to at least try it on, like, a couple of reactions. And if you get to where you're doing, like, 30 of these 30, not exercises, but, like, 30 minutes of this a day, you're going to start cycling through those reactions. You're going to see them a lot. And also, I would say, as much as you can this weekend, try to get all the reactions down pat, because you don't want to be having to learn all the basics for all 80 reactions next weekend on top of another problem set and the practice exams. So, do what you can with it. Now, all this being said, I know I started 10 minutes late because we started on Harvard time waiting for, like, more people to show up. I still want to do the synthesis with you, but it is time. So if you have to go, you have to go. This synthesis is hard. It's the hardest one you've seen in the class so far. And so it will take at the least 15 minutes. Normally, I budget between 15 and 20 minutes. So you are welcome to stay for it. It's a full challenge problem, but I want to make sure it gets into the recording. You're also welcome to leave if you need to. No worries.
Thank you for doing it.
Yeah, no, totally.
But the video will be on.
Yes. So, okay. Challenge problem 10. Woof. This is going to be like a 9 or 10 step synthesis, and we have so many reactions already that it's hard to be thinking through all of this. So, after we panic for a minute, we take a breath, and we start with our functional group analysis. Take a minute, circle all the functional groups, and label them. How'd you do? I think the trickiest one is this one up here. They're neighbors, a BR and an OH, so they're not separate. They're a halohydrin. They're hard to spot. So now, if we have a halohydrin, we only really know one reaction of halohydrins, right? So why don't we go ahead and turn her into our epoxide, since, like, we don't know where anything else is going, but, like, that's kind of the only thing we know how to do with this. So, we have formed an epoxide. Now, after this, we have some brainstorming and mapping, and we can go in whatever order. I want to do some mapping, because this, I feel kind of unmoored. So, we look for characteristic parts of the molecule. One characteristic part for me is this big phenyl ring. I feel like that's got to be this pH down here, right?
Yeah.
Okay. So then what I'm going to do is I'm going to look at the carbon next door to it. And this next door carbon, I'm going to call red star. So red star, if I go next door to the pH on the bottom, is going to be one of the carbons here on the alkene. Okay. Then another characteristic point, I think, are the two methyls here, right? And then I'm going to call the carbon right next door to that green star. So if I have my two methyls here, the carbon right next door is green star. Do you buy that mapping? So one of our big goal of the reaction is we need to connect red star and green star. We need to make a carbon-carbon bond, which in all of organic chemistry, especially for this first semester, you only know a finite ways of making carbon-carbon bonds. But let's do a little bit more analysis. So like another functional group that we don't know a lot of ways to make are alkenes, right? So alkenes, we really only know E1 or E2. And so let's think about what that's going to look like before we do the elimination. So we have OET here. We have our 2 methyls. And before the elimination, it's going to look like either a leaving group on the left side or a leaving group on the right side. Just because we need some sort of leaving group that's either going to leave, make a carbocation, then we do elimination E1, or we need a leaving group that's going to do an E2, like anti-pyropaner elimination. And we don't know which one it's going to be. But do you buy that, like, we're going to need to get one of these arrangements of some leaving group present? Yeah.
Sorry, can you explain how those would be a different mechanism? The was like on the top or the bottom?
It's not necessarily a different mechanism. This is just the different layout. So, like, if we made a double bond here, we needed to have had a leaving group either on that position or that position.
Oh.
And it's not really about E1 or E2 here. It's just, yeah, that we have to have some sort of leaving group. Yeah. Okay. So we have this goal of the carbon-carbon bond. And one thing that's going to guide us is we want to have a good nucleophile and a good electrophile coming together. So if we already know over here this green star girl is going to be turned into an epoxide. Are epoxides nucleophiles or electrophiles? Electrophiles. We crack it open. So somehow we need to turn our carbon on the OH into a nucleophile. So really quick, let's brainstorm. What are all the different kind of reactions that we could do with an alcohol? Yeah, we could do all of our leaving group reactions. So we can make it into a chlorine, a bromine, a tosyl. Other reactions with alcohols. Like? Oh, last lecture you're thinking about concanate. E1?
No, to like when you go to the aldehydes and carboxylic acids.
Redox family. So we can take it to an aldehyde, we can take it to a carboxylic acid. Yeah, CADS family, yeah. Or this specifically, we're going up and down oxidation level, so it's redox. But then we can also do some CAD reactions, like this could be an alcohol, we could do stuff with esters. We could do acetal. We could do E1 elimination. Like, there are lots of things now. With an alcohol, we have many options. And then once we get to each one of these different groups, then we have a bunch more branches here. So let's just start with this. But then if we're thinking about our goal, we need to make this red carbon a nucleophile. Where have we seen carbon nucleophiles? Yeah, like our Grignard. So when we had a Grignard reaction, she is a carbon nucleophile, right? Like our R with its electrons. So, okay, well, if we wanted to make this into a Grignard, MgBr, how do we make a Grignard? It's made from what functional group?
A ketone or aldehyde?
No, that's what it attacks. It attacks a ketone aldehyde. But we make it from a bromine, and then we like add our magnesium, right? Can we turn alcohol into a bromine? We did it today. Whoa.
Why did you decide to do Grignard?
Because we needed a carbon nucleophile. Like, we need this carbon to somehow attack this. And right now, it's not a nucleophile. The only carbon nucleophiles we know are like RMGBr. That's a carbon nucleophile that can go and attack for our R group. Or R lithium. Those are really it. We technically have a CN minus. That can be a carbon nucleophile. but we don't have any like nitrile stuff here. So let's do this. We have our alcohol that we want to turn into a bromine. So we use our PBr3. And then we want to turn that bromine into a Grignard. And we use magnesium and ET2O. So now our red star carbon has become a nucleophile. Cool. Seems like we're ready to connect them. The only thing to check with the epoxide is Grignard acid or base? It's a base. So bases, do they attack the more or less substitute side of an epoxide? Less. And is that what we want?
Yes.
Yeah. Okay, great. Moving on. So we combine them. ET2O. And then we do an H plus workup. And when we do that, we have our epoxide OH here. Then we have our red star, or sorry, our green star here, which is next on the epoxide, attached to our red star, which was on the Grignard. And we've made our carbon-carbon bond. Great.
Wait, so what was the number one? What was that say?
Combine with ET2O. So now at this point, we need to make this into an ether, which we could do like Williamson ether, and we need to do elimination, but didn't we say we need to have a leaving group on one of these carbons? And now this is just an alkane, right? We lost them. It was a good one. We have our first dead in the water synthesis strategy. We salute you. You've taught us so much. You've taught us so much. We got valuable information about what doesn't work. Whatever we do, we have to figure out a way where we have two functional groups on adjacent carbons. Like we need, if this carbon right here, if we can't make a functional group on her because she's our nucleophile going to attack, we need a way to have another functional group here. And whenever we need two functional groups next door, we should be thinking about our epoxides. If we go back and look at these, all of these other reactions other than the Grignard put two functional groups right next to each other, right? So let's try to do one of these other ones, and then we'll have two functional groups, right? Well, I mean, reactions that we haven't done yet, other goals. We have make the alkene, which we can't really do until we have the stars connected yet. And then we have to also make the ether, which I guess like that's another goal we could try working on. How could we make an ether on the right side over here? We wanted to add an OET. Well, if we're adding on this, I said the right side, I meant the correct side. So if we wanted to add an OET on this side, the more substitute side of the epoxide, do we need acid or base? Acid. So let's try that. So we're adding our HOET in acid. So that's going to make an OET over here. And on the carbon next door, we have an OH from the epoxide. We have two functional groups, right? Okay. Well, now, this carbon's not an electrophile, is it? So we need to make this into an electrophile for Grignard to attack it. Because now we have our ether, we have the two functional groups. We have a lot of things working. Well, what do Grignards normally attack? Yeah, could we turn an alcohol into a ketone or aldehyde?
Yes.
So this is another really cool synthesis idea. Alcohols, you can turn into nucleophiles like Grignards with a couple steps. You can also turn them into electrophiles by oxidizing them. Ooh. So we could do CrO3 and pyridine, and now we have an aldehyde here at our green star carbon. We have an electrophile again. So now let's try combining these and we see what happens. So if we combine an ET2O and do an H plus workup, then we have OET here. At our green star carbon, when a Grignard attacks a carbonyl, what's left there?
ROH.
It's turned into an alcohol. Like initially it'll be an O minus, and then our acid workup we protonate it. So we have an OH here. And then we have our red star and our pH. So now are we in one of our scenarios here where we could do our final, like making an alkene? Yeah, we have something that could be a leaving group here. Right now, OH is not a very good leaving group, right? So we need to make it a better leaving group. So we're in this version, not this one. We can either do an E1 route or an E2 route. Which do you want to try?
E2.
Let's just do E2. I think E2 is a little safer. E1, we would have carbocations. We have the potential to rearrange. So we need to turn our OH into a better leaving group. What's your favorite one? I meant of like the three, like, yeah. Yeah, any of them. I heard PBR3, so I'll go with that, but either of them could work. So now we have a bromine here, OET. We have a good leaving group, so to do an E2, all we need is a base. So let's just use like Naomi. Now, how can we control that the double bond adds on this right side instead of the left side? Does this have any beta hydrogens? No. So the only option is to form the alkene we want. And hey, that helps us with synthesis. We didn't have another dead route. So this is it. If we look at it, it's 1, 2, 3, 4, 5, 6, 7, 8, 9 step synthesis. This right here is a different game than the synthesis for the first test. This is putting together reactions from every lecture you've learned so far, and you're having to think in much more abstract terms. This type of question that we are going to ask you on exams is why the basics have to be cold. They really, really need to be ingrained, because otherwise this becomes nearly impossible to do in 15 minutes. But I hope it was helpful kind of seeing this and talking through some of the logic of it. We have some tools we're studying now. We've kind of recapped a lot of the functional groups for Lecture 7. So I hope you all have a good weekend. Thank you for coming to section. And I'll see you on Monday. Oh my gosh. Thank you.